Okay, so this question is from October-November 2016, paper 42, right? And this question is related to spectroscopy. So let's start the question. They're saying that compound F is a carboxylic acid. So we have some compound F, which is a carboxylic acid. It contains 31.4% oxygen by mass, and its mass spectrum has a molecular ion peak at mass to charge value 102. So it contains 31.4% oxygen and its molecular ion peak is at 102. Use all of this information to show that molecular formula of compound F is C5H10O2. Show all your working. Okay, so we just have to prove that its molecular formula is C5H10O2. The percentage of oxygen is given and the molecular mass, because this is the molecular ion peak. So that means this would be the Mr. This is the Mr of the molecule. So if we just calculate the 31.4% of 102, then we get the mass of oxygen present in this compound. So 31.4% of 102, that is around 32. So that means it has 2 oxygen atoms because the atomic mass of oxygen is 16. All right, so we have 2 oxygen atoms, and then if we subtract the mass of oxygen from the total mass, 102 minus 32, that would be 70. So 70 means 5 carbon atoms, that would be 12 into 5, 60, and 10 hydrogen atoms. 1 into 10, so that is equals to 70, so that means 5 carbon atoms and 10 hydrogen atoms. Okay, so the molecular formula would be C5H10O2. All right, so the next question is, there are 4 possible structural isomers. 4 possible structural isomers of C5H10O2 that are carboxylic acids. The first isomer has been drawn. Draw the skeletal formula of the 3 other structural isomers. Okay, so we have to draw 3 structural isomers of C5H10O2 and they all must be carboxylic acid. Okay, so we have 5 carbon atoms. The first one, they have drawn the 4 carbon atoms in the chain. If you can see here that these are 4 carbon atoms, 1, 2, 3, 4, 4 carbon atoms in the chain, and this carbon atom is on branch. So the simple structure would be if you attach all the 5 carbons in the straight chain. So 1, 2, 3, 4, 5, double bond O, OH, this is one isomer. And then what if we change the position of this methyl group in 4 carbon atoms chain? So 1, 2, 3, 4. If I change the position, then it would be on this carbon atom. And if we take 3 carbon atoms in the chain, this is Protonoic acid and 2 of the methyl groups on the same carbon atom. So these are 3 isomers. The one of the isomer was already drawn. We have drawn 3 isomers, all are carboxylic acid, and their molecular formula is C5H10O2. Okay, next part is state the systematic name of isomer 1. Isomer 1. Now this is isomer 1 and this is a carboxylic acid, right? This is isomer 1. So first of all, we have to name the number the chain, and you all know this rule that in carboxylic acid, numbering always start from the carbon of the carboxylic acid, carbon of the functional group. So this we always give this carbon the priority, this one, right? The carbon of the carboxylic acid. This is carbon number 1, carbon number 2, carbon number 3, carbon number 4. So that means second carbon has a branch, and because there is only 1 carbon in the branch, that means it is methyl. So 2 methyl and 4 carbons in the chain. So that means it is butanoic acid. 2 methyl butanoic acid. All right, now the next part is from C13 Nmr spectrum. F is one of the 4 structural isomers in B1, the 4 isomers that we have drawn here. So this is either one of them. A carbon 13 NMR spectrum of F is shown. So this is C13 NMR spectrum of one of the isomers which we have drawn above. Use the spectrum to identify isomer F. Draw its structure in the box below. Okay, so we have to identify the structure F. Now, how many peaks do we have in this spectrum? This one is from tetramethylsilane, the reference material, right? So we will not count this one. So then we have 3 peaks, 1, 2, and 3. 3 peaks. So that means 3 different carbon environments. So in which structure do we have 3 different carbon environments? If you can find out, like in the first structure that we have drawn, all the 5 carbon atoms is different. 1, 2, 3, 4, 5. So no, there are total 5 different carbon atoms. So we get 5 peaks in the C13 Nmr spectrum of this molecule. So this could not be the one which we have below in the question. Now, if you look at this compound, isomer 4, so this is a different carbon atom, 1, then this is a different carbon atom, 2, then these 3 are same because they are all attached to the same carbon atom. So this CH3, this CH3, and this CH3, they're all same. So that means third peak would be due to these. So total 3 peaks, 1 for these, then second for this carbon atom, and third for this carbon atom. So total 3 peaks. In this structure we have 4, 1, 2, 3, and 4. These 2 are same. These 2 are same. And in this one, 1, 2, 3, 4, 5. 5 peaks. So 5 peaks for this one, 5 peaks for this one, 4 peaks for this one, and this one would give 3 peaks. Alright, so the structure of the isomer which gives 3 peaks on a C13 NMR spectrum, that is this 3 carbon atoms in the chain and 2 carbon atoms in the branch. Alright. Now, the next part of the question is use the data booklet and your knowledge of carbon 13 NMR spectroscopy to identify the environment and hybridizations of the carbon atom responsible for each of the 3 absorptions. Right. So now we have to give the environment of the carbon atom and the hybridization. And for environment, we have to look into the table. Now, from this year, you would get the table in the question, as there is no data booklet from this year. So they'll give you the table of C13 NMR in the question. Right, but for now, let me just have this here for you. All right, so this is the table for C13 NMR. This is the structure, and we have to write the environment of the carbon atoms and the hybridizations. Chemical shift values they've already given us, right? So first value is 27. So 27, if you look into the table, that would be this alkyl group. It's range from 0 to 50. So it would be an alkyl group, right? And that would be these 3 carbon atoms. These 3 carbon atoms. They would give a peak on 27 parts per million. So the environment of the carbon atom, that we can say it would be an alkyl group. Alkyl group, and the hybridization, because we are talking about these carbon atoms. These 3 carbon atoms. Right, so what is their hybridization? They are attached to 1 carbon and 3 hydrogen atoms. So they are making 4 single bonds, total 4 electron pairs. So that means hybridization is sp3 hybridization, no pi bond. All right, G. So the next peak is at 41. And the peak at 41 would be due to this carbon atom, the carbon which is directly connected to the carbonyl carbon. If you look in the table, the third row, this is this. Next to carbonyl, it ranges in 30 to 65. And we have the peak at 41. So it comes in between 30 to 65. So that means this peak is due to carbon next to carbonyl group. All right, and the hybridization of this carbon atom, this would also be 1, 2, 3, 4 sigma bonds. So this would also be sp3 hybridization. And the last carbon atom is carbonyl. So that would be carboxyl. This, and the range is, or the chemical shift value is 179. And this comes in the range 160 to 185. So that means it is carboxyl group. And the hybridization of this carbon is 1, 2, 3. So it has total 3 sigma electron pairs, one is pi bond. So the hybridization would be sp2. So this is how you have to fill the table: the environment of carbon atom and the hybridization of the carbon atoms. All right, now the next part of this question is related to the proton NMR. So G is another of the 4 structural isomers in B1, the 4 isomers that we have drawn in the first part. The proton NMR spectrum of G is shown. So this is the proton NMR spectrum. And as you can see, this is a high resolution proton NMR. We have this doublet, then again a doublet, this is a multiplet, and this is singlet. Right? All right. Now they're saying that use the data booklet and the spectrum to complete the table below. Data booklet and the spectrum to complete the table below. The actual chemical shift of the 4 absorptions in G and the splitting pattern. The chemical shift values and the splitting pattern at 1.6 ppm. This one. Multiplet. This one. So its chemical shift value is 1.6. So this have been added for you. Right, so we have chemical shift values, we have to write the type of proton, the number of protons, and the splitting pattern. Okay, so first of all, let's just fill the splitting pattern. 0.9, this is the peak at 0.9. So this is a doublet. Then 1.6 is already filled. This is 1.6 multiplet. 2.4, this is 2.4, again a doublet. And 11.5. So this one is 11.5. This is singlet. All right. Now, next we have to write the type of protons and the number of protons. So for that, we have to look into the table. Okay. So this is the table for the proton NMR. And we have to fill these 2 columns, type of proton and number of protons. But before that, we have to find out what structure do we have. Like we have 4 different peaks in proton NMR. So there's 4 structures that we have. First, we have to decide which structure is giving this spectrum. So the first structure that we have is 1, 2, 3, 4, 5. Butanoic acid. And if we look into butanoic acid, how many peaks can we get on a proton NMR? 1 peak due to this hydrogen atom, 1 peak due to these 2 hydrogen atoms, then 1 for these 2 hydrogen atoms, 1 for these 2 hydrogen atoms. This is peak number 3, peak number 4, and peak number 5. So that means 5 peaks on a proton NMR. So this cannot be the structure for which they have given us this spectrum, right? The other structure that we had is butanoic acid, in which a methyl group is attached to the second carbon atom. So how many protons do we have in this? How many different protons we have in this structure? 1, 2, 3, 4, 5. Remember, this CH3 and this CH3, they both are different because this CH3 is attached to CH2, this CH3 is attached to CH. So they both are different, right? So 5 peaks for 2-methyl butanoic acid, sorry. Now this next structure that we have is butanoic acid, and methyl is on 3rd carbon atom. So now how many peaks do we have? 1 for this proton, 1, then 2, 3, and these 2 hydrogen atoms, this CH3 and this CH3, they both are attached to the same carbon, so they would give the same peak. So 4 peaks. In total, we get 4 peak. So that means our structure is 3-methyl pentanoic acid, right? 3-methyl pentanoic acid. So now let's just fill the table. So type of proton for the peak at 0.9 ppm. So type of proton, it would be an alkane, because 0.9, this is the only range that we have, 0.9 to 1.7, so that means it would be an alkane, right? So I've already written it here. This would be an alkane, and number of protons responsible. Now 0.9 CH3 or CH, so this is a doublet, right? So this is a doublet. So if you look at this structure, now these two alkanes, they are attached to CH. That means the splitting pattern, I hope everyone know this thing, that splitting pattern is due to the number of protons on the neighboring carbon, number of hydrogens on the neighboring carbon, or number of protons we can say, but number of hydrogens on the neighboring carbon, right? So at 0.9 we have a doublet. So that means the neighboring carbon atom has only one hydrogen. So if you look at this carbon, it has only one hydrogen. So this CH3 and this CH3, they both would give a doublet, right? So this is our required structure. This would give a doublet. And how many hydrogens are responsible? 3 and 3. In total 6 hydrogens are responsible. So number of protons would be 6. Then at 1.6 we have a multiplet. This is 1.6, right? Let me change the color of the marker. So this is 1.6, and we have a multiplet. So multiplet would be if we have more than 3 hydrogens on the neighboring carbon atom. So if we look at this carbon, again this is an alkane. This is attached to this carbon atom which has 3 hydrogens, this carbon atom which has 3 hydrogens, this carbon atom which has 2 hydrogens. So this carbon would give a multiplet, right? And how many protons are responsible? 1. So the multiplet is due to number of protons 1, and type of proton is again CH, or you can write alkane. Okay. Now the next peak is at 2.4. So at 2.4 again we have a doublet. Here. And if you look at these two peaks, which two peaks? This peak here at 2.4 and this peak here at 0.9. The peak at 2.4 and the peak at 0.9. If you compare the peak height ratio of these two peaks, the peak at 0.9 is 3 times that of peak at 2.4. Right, this peak is 3 times of this peak. Right, so that means if this peak has 6 hydrogen atoms, so this peak would have 2 hydrogen atoms, because there would be 3 times less number of hydrogen atoms, right? So it would give a doublet and would have only 2 hydrogen atoms. So if we look at this carbon here, this has 2 hydrogen atoms. This is CH2, and this is attached to this carbon atom which has only 1 hydrogen. So it would definitely give a doublet. And on this side, on the right side, there are no hydrogens. So this CH2 would give a doublet, and it has 2 protons responsible. So type of proton is CH2 and number of protons are 2. And then finally we have a peak at 11.5, and the peak at 11.5 would be due to the carboxylic acid. If you look into the table, let me just erase it. Okay, so this is carboxylic acid, and if you look at the peak range is 9 to 13. So it comes in the range 11.5, so that means it is due to the carboxylic acid, or COOH. Number of protons responsible 1. Deduce which isomer is G and draw its structure in the box. So we have already drawn the structure. Let's just draw it here as well. So this is COOH and we have a branch here, right? So this is 3-methyl butanoic acid. And now the last part is name or give the formula of a suitable solvent for obtaining a proton Nmr spectrum. So normally in a proton Nmr spectrum, the solvent we use is CdCl3. D is deuterium, the isotope of hydrogen, and it does not give any peak on proton Nmr.